our photographs?
Hmm? Oh, yes. Here we are. Now, that's the first one.
This was in sunlight?
Yes, that's right. He sealed a photographic plate in black paper, small pile of uranium salts on top, and that's the mark it made right through the paper. That's the really interesting one. That's the one he left in the drawer over the weekend.
And no sunlight fell on it, so it's not phosphorescence.
No. There's no apparent source of energy for producing the rays at all. But that contradicts the law of conservation of energy.
What's the longest he kept the uranium salts in the dark?
I'm not sure. Over 6 months, anyway. And they were still active.
Extraordinary.
Well, where are you going to start, then? Becquerel covered a lot of the ground.
Yes, but only with the salts of uranium and fluorescent compounds. It may happen with other substances as well. I mean to test everything. I examined all the known elements, either in their pure state or in compounds, to discover if there were other elements with the same property as uranium. I needed to employ a precise quantitative method in order to go beyond the results reached by Becquerel. I used the excellent method developed by Pierre and Jacques Curie, the Curie electrometer.
Five o'clock.
Pierre, come and look at this.
Oh, it's freezing in here.
Oh, no. 6.25 degrees. I can hardly feel my feet at all. Never mind. Have a look at this.
But it isn't uranium.
No. It's a compound of thorium. But it's giving off the same rays. It is, isn't it?
It would appear so. Thorium.
It is the thorium. I've tried 2 different compounds. Months or years, you said it may take, but 6 days. I am right, aren't I, Pierre? There's no possibility there could be a mistake.
No. Not at all. Congratulations.
Do you think any of the other elements are likely to have this, what do you call it?
Well, we thought radioactivity. No, apparently not. She's tested every known element.
Oh, so she's stuck there.
Oh, far from it. This week, she's been testing uranium in different compounds and under different conditions to find under which conditions radioactivity is highest. Look what she got. There, that column on the right.
So they're all much the same.
Yes.
Isn't that what she expected?
No, it shouldn't be like that. Not under different conditions. It doesn't fit in.
With what?
Everything we know about energy and matter.
Well, it looks as though it must have something to do with whatever all these have in common.
Precisely, but that's the point. They've nothing in common. Only the actual uranium atoms. But an atom can't produce energy.
I see. So it doesn't seem to lead you anywhere, then, huh?
Not on its own.
Oh, what do you propose to do?
I shall go on collecting facts until I find some explanation. Pierre, you know that table I worked out for the radioactivity of uranium? Well, assuming that that was correct.
It was correct.
Well, using that as a comparison, I tested a sample of raw pitch blende this morning. It's 4 times as radioactive as uranium.
But that means that radioactivity cannot be an atomic property after
I know.
all.
Unless there's something else in the pitch blende, apart from the uranium and apart from the thorium. Something else again.
But what else could it be? You proved yourself that none of the other elements are radioactive.
I know. None of the known ones.
Marie...
Something else, that's all I said, some other substance. But I think it must be a new element. What else can it be?
How much bismuth does your sample contain?
Oh, quite a high proportion, we think.
Well, there's the bismuth spectrum.
So, if there are any additional lines on our plate...
That'll be your polonium, unless there's some other impurity there. I'm sorry, madame.
Oh, isn't that something there?
Not really, I'm afraid. Still, we knew it was only an outside chance. A new element is a rare event.
Perhaps there wasn't a high enough concentration.
It's possible. I can't always get clear lines with a known element. You could still be right.
We are right, Monsieur de Marseille.
Marie, we still haven't explained why pitchblende is 4 times more radioactive than uranium. The polonium's active, but not active enough.
Could it have lost activity as we purified it?
No, it doesn't seem right.
No, it doesn't.
Oh. We must have made a wrong measurement somewhere.
Not necessarily.
What do you mean?
What if there was something else in it as well?
If you're going to make a habit of discovering a new element every 6 months, there'll be enough room for them in the periodic table.
But it could have happened.
All right, I know. But we'll do some tests.
Well, let's hope for a better result than we got with the polonium. Have you got a name for this one?
Radium. Even that sample, which we think is mostly barium, is 400 times more radioactive than uranium.
And there we have the barium.
And what's that?
Oh, that's your radium.
In our laboratories today, we live in an atmosphere dim with the flying fragments of exploding atoms. And on this occasion, I wish to say a few words on the methods and ideas employed to break up atoms and to realize...
Lord Rutherford of Nelson, with little doubt the greatest experimental scientist of the 20th century and the founder of nuclear physics. Perhaps most of all, he was influenced by the man who directed the lab at that time, Professor J.J. Thomson. Thomson drew his pupils' attention to the new discoveries in radiation. Rutherford became fascinated in the work of Becquerel on the strange new properties of uranium. The young student set up simple apparatus to examine this radioactivity.
Well, I'm afraid this isn't a very glamorous object. It is, in fact, a gold leaf electroscope and is the sort of thing that Rutherford used in his early work on radioactivity. It's a thing for measuring radioactivity. Inside, there's a gold leaf that stands out like that, and when you put a piece of radioactive ore under the thing like that, then the gold leaf loses its charge and collapses. He showed that in doing this, the radioactive substances gave off more than one kind of particle. He put his piece of ore underneath, and then he put absorbers in between, pieces of paper, pieces of aluminium, and showed that some of the particles were more penetrating than others, and there were 2 kinds. There were alpha particles and beta particles.
Rutherford, through the brilliant directness and elegance of his experiments, had made the first step in the understanding of radioactivity, and he was to devote the next years to developing a total theory. Very quickly, he discovered something of great significance, that the radioactivity of a solution of a thorium salt was different when the lab door was open from when it was shut, that it was affected by drafts. For Rutherford, this was remarkable, and he set up an elegant little experiment to examine it. To simulate a draft, Rutherford passed air through a solution of a thorium salt, and the air was collected after drying and examined for radioactivity. The air was very active, and there seemed only one possible conclusion, that the thorium was giving off a radioactive gas. This seemed extraordinary, since thorium was known not to form gaseous compounds. It was this experiment and those that followed it that led Rutherford to the idea that radioactivity involved the decay of one chemical element into another. In 1904, he published his conclusions in what has now become a classic text. He showed that the alpha and beta particles he had earlier discovered resulted from atoms actually breaking up and forming smaller atoms. And he demonstrated that the amount of energy released in this breakup was enormous. But this idea of transmutation was regarded as unacceptable.
You can't change one atom into another in 1900. It's quite impossible. But what Rutherford and studies showed was that nature was doing that in a few cases when the atom was extremely heavy, like uranium and thorium and radium.
Within a few months, Rutherford's ideas were widely accepted. As ever, he continued his investigation into alpha particles, radioactivity, and the structure of matter. In these experiments, he used chunks of dangerously strong radium, and radioactivity still marks the site of his work. And here in 1908, he directed a series of experiments which formed the whole foundation of modern nuclear physics.
He'd got these fast particles given out by radioactive materials, the alpha particles, which he thought of as kind of bullets or shells that he could shoot at things. And he went round in rather a sporting spirit, really, shooting these minute projectiles at things to see what they were like and what they would do. And he found, you see, that when he fired these alpha particles, these projectiles, at a very thin film of paper or aluminium, that some of them, he didn't mind them being deflected, he'd expected this, but some of them came backwards, deflected through large angles. He said, I was as surprised as if a 15-inch shell had been turned backwards by a sheet of paper. It was an astounding thing, and it meant that these things must be making very close contact with something rather massive. And from this, by very simple mathematics, he was able to show that there must be this small, massive nucleus in the middle of the atom. Quite completely new vista of ideas.
The atom, previously thought to be uniformly solid, was now shown to be over 99% empty space. Nuclear physics was founded. But now in 1914, Rutherford thought he had reached a limit. The nucleus, he thought, could not be probed further. A page of scribbles of fundamental importance, the first experiment in which an atom was split.
The interest in bashing the atom and changing it into another atom was so enormous to the scientists on theoretical grounds that really it didn't matter a blow if in 25 years' time it was going to earn you a dividend or anything of that kind.
At the extremely high cost for the Cavendish of nearly £1,000, they built an apparatus for artificially accelerating hydrogen atoms under huge voltages. It was constructed from old petrol pumps, odd pieces of metal, and a couple of tea chests. It was designed to achieve a next stage in nuclear physics, to artificially split atoms down into alpha particles. But no one knew whether it would work. Professor Walton remembers the first tests with Rutherford.
We brought him along here, and after a certain amount of trouble, we maneuvered him into this hut. He was a big man, looking perhaps a little bit more like a gentleman farmer than the popular idea of a university professor. However, he sat down on a little wooden box there, and he peered into the microscope and gave instructions to us as to what to do. He'd say, raise the voltage, or increase the proton current, or cut off the proton current. He didn't pass any comment, and after a while, he told us to switch off the voltage and let him out. So we got him out of this, and he got up, and he sat down on a laboratory stool. And he said something like this. He said, well, I've seen some scintillations there, and they look just like the alpha particle scintillations from a radioactive substance.
The triumph immediately became news. Rutherford and his pupils were paraded in front of the press, and numerous speculations were made on what the work meant. Throughout the 30s, Rutherford was to admit to no practical applications for his work. He maintained the image of the simple scientist. And about the most practical thing he ever did was to allow his name to be used on a train. Someone said, Rutherford, you're on the crest of the wave. Rutherford replied, I created the wave, didn't I?
I love physics. I can hardly imagine it not being part of my life. It is a kind of personal love, like one has for a person to whom one is grateful for many things.
In 1907, a shy young woman named Lisa Meitner arrived here at the gates of this university. She had traveled here from Vienna in order to further her education in physics. She particularly wanted to attend the lectures of one of the professors here, Max Planck. She came from a rather liberal, middle-class Viennese family, with parents who wanted all their children to have a good education, not just the boys. Lisa spent some time preparing for the only career then open to women, school teaching. But in 1897, the University of Vienna decided to admit women. She enrolled and became one of the very first women in Austria to get a science degree. Her physics teacher was the great scientist Ludwig Boltzmann. He was engaging, energetic, warm-hearted, and Lisa Meitner always remembered his lectures as the most beautiful and stimulating that she ever heard. She came away with a vision of physics as a battle for ultimate truth, and it was a vision that she never lost. But still, the only career open to her in Austria was school teaching. So she persuaded her parents to continue her allowance for a few more terms, which would let her come and study in Berlin. She began to meet a number of new friends. One of these was a young chemist named Otto Hahn. That meeting was to alter both their lives profoundly. He was working in an area that Lisa Meitner was interested in, radioactivity. So the two of them began working together and started looking for new, previously undiscovered radioactive substances. At the time, women were not allowed in the chemistry laboratories, so Meitner and Hahn had their own small room, which had previously been a carpenter's workshop. They found that they got along well together, and in the years that followed, they published a number of scientific papers. But Meitner's position remained unofficial. She did not get a salary. She was still living on the small allowance from her parents. But an important development occurred in 1912 in Dahlem, a quiet and leafy suburb out to the west of Berlin. The new Kaiser Wilhelm Institute for Chemistry was nearing completion, and Otto Hahn was offered a post here as professor. The new building was important because their old labs had become thoroughly contaminated with radioactivity. Here in their clean new laboratories, Meitner and Hahn decided upon a terribly difficult new project. They would look for something that had never before even been detected, the mother substance of the element actinium. Actinium was the least well understood of the radioactive elements. From what was known of its chemical behavior, however, it was assigned to group 3. The radioactive elements formed a sequence. There's radium here in group 2, thorium in group 4, and here in group 6 was uranium, the heaviest of all known elements. What was missing entirely, however, was any evidence of an element here in group 5. Now, during the process of radioactive decay, elements are transformed from one into the other. There's only two ways this can happen. Either an element can move one place to the right, or an element can move to a new element 2 places to the left. Actinium was never associated with radium, so radium could not be the mother substance of actinium. Instead, Meitner and Hahn decided to look here, in group number 5, for the missing mother substance. They started to set up some experiments to try and find the mother substance. On the 16th of March, 1918, Lisa Meitner and Otto Hahn submitted their paper, The Mother Substance of Actinium, a New Radioactive Element. It was, especially considering the difficulties, a terrific achievement, and it gave them great prestige. They decided to call the new element protactinium. The gap in group 5 was now filled. Lisa Meitner was promoted. She was made a professor. She was given her own department, her own physics section here in the Institute. The 1920s were good years for Lisa Meitner. In her department, with her students, she carried out pioneering experiments on the composition and behavior of the atomic nucleus. Albert Einstein nicknamed her the German Madame Curie, and Otto Hahn was quick to admit that it was Lisa Meitner's department that brought most international recognition to the Institute. Uranium was, at the time, the heaviest known element. It looks like a normal metal, but its nucleus is large and unstable, and it's radioactive. But work done in Rome, which involved bombarding uranium with neutrons, had suggested the possibility of an even heavier and therefore unknown element being produced. Back in Berlin, intrigued by the possibility of discovering another new element, Lisa Meitner persuaded Otto Hahn that the two of them should once again work together. They were joined by a third person, the chemist Fritz Strassmann, as they set to work to unravel what they called the uranium problem. From 1934 until 1938, the team worked hard at the problem, irradiating uranium samples with neutrons, and then trying to identify exactly what they had produced. The results were complex, but at first it seemed that they were producing not one, but several new elements beyond uranium. In fact, they were very close to a discovery that would be much more surprising than anyone expected. In November, he wrote to tell her of a puzzling result. Their bombardment of uranium seemed to be yielding not a heavier element, but a lighter one, radium. Just before Christmas, she received another letter from Hahn.
Our results are so peculiar that for now we shall tell only you. Our radium isotopes act like barium. Perhaps you can come up with some fantastic explanation. We ourselves know that it can't actually burst into barium. You see, you will do a good deed if you can find a way out of this.
For uranium to change into radium would mean moving 4 places to the left. This was difficult enough to explain, but the barium result seemed ridiculous. Barium lies 36 places to the left. Either this was a mistake, or something quite extraordinary was taking place. For some years, people had thought of the nucleus not as a hard thing, but as a liquid drop. Meitner and Frisch realized, at this moment, that when a neutron hit the nucleus, it could become unstable, that it might elongate, and split into 2. They also realized at this moment that when it split, it would be accompanied by the release of a tremendous amount of energy. Otto Hahn's strange experimental results could now be explained. The uranium atom had split into 2 smaller fragments, one of which was barium. It was at this moment that the world moved forward, as yet unknowingly, into the atomic age.